everyone. Let me check my sound levels. Looks good. 10 viewers looks good. Okay. Um, so let's start. Let me tell you what's on the test and and how many questions and so on. The test will cover Newton's laws, and it'll cover statements of Newton's laws and also solving problems with Newton's laws. And it'll cover that shorter section which was on Newton's universal gravitational law and also Kepler's laws and the energy stuff. Okay, and it's 28 questions long, you should be able to do that within an hour. But like I said in my email, I'll give you 2 hours. And a few people have said that there's some conflicts, so it'll probably be open earlier than your class time. You can start it early if you like. I'll tell you what the times on the day of the test, because I got to sort of work out exactly when to start each one. And but no matter when you start it, you'll have a full 2 hours. Okay. And that's about it. It's the same format as last time. When you do the test, you won't see the answers right away because the tests are straddled, and if someone knows the answer, they can share them with someone else. But I'll make the answers available so that you know what you got right and what you got wrong. You'll get your grade right away, but which ones were right and which ones were wrong. You'll get that probably the Monday after or something like that. Okay, or maybe even on the weekend. And so just like last time. All right. So what we're going to do today is we're going to do everything, but I can't squeeze in energy problems. Okay, but that's okay. We just did energy problems um, last week, and if you really want to see another energy problem, you could watch the Physics 101 streams tomorrow. I don't think I'm going to do any calculus during those, so it'll probably be just straight problem solving. So that'll be okay. And if I do, maybe I'll just mention, hey, this is calculus. It's not part of your stuff. But when they solve their problems, they're just like your problems. The only difference is that I expect them to understand the calculus proofs behind some of the stuff they do. But I think you'll be okay. So let's start with the solving the problems today. So let me move this down so you could see around my image here. Can you see that? Yeah, you should be able to see that. Okay, so the first question actually is incomplete because I didn't fully write it out. I'm just going to show you the picture. But what I want you to calculate in this picture is the acceleration, the direction of the acceleration, and the tension in the rope. Okay, so I didn't write out the English because I'm just going to show you the diagram. Here it is. So we haven't done one of these before. This is a double inclined plane. Usually we did ones where there was a single inclined plane and just one mass, or a single inclined plane and two masses where one was dangling straight off. But I decided to do one which was just two. It's it's not that much harder. Okay, it's not that much harder. And so just for variation, I thought I'd do this one. Okay, and so we have the 7 kilogram on this inclined plane, which is at 40 degrees, and this other 10 kilogram at 30 degrees, like that. And I want you to calculate the acceleration. And for question number one, let's assume there's no friction. Okay, and I'll go. I don't want to go too fast, but I'll go a little faster so that we don't get caught up in all the details, because you've done quite a few of these, and so it's pretty obvious how to proceed. So the first thing, let's start with the 7 kilogram, and let's identify all the forces on it. And gravity, gravity technically is straight down, and it would be 70 newtons. Okay, but because all the other forces are on an angle, we're not going to do it that way. We do it the way we always do. We're going to break it up into a perpendicular component and a parallel component, like that. Now, something that students sometimes get confused with is the formula is mg, either cosine or sine theta, and they always forget which one's which. And so this one is the cosine. Okay, so the perpendicular component is the cosine, and the parallel component is the sine. Okay, so there we go, sine theta, like that. All right, and that's the formula where m, actually I should call this one m1, and I should call that m2, because if you've got two masses, you don't want to confuse them. So this is actually m1g, and that one is actually m2g. Okay, and you can even call this theta 1 and that one theta 2, because you've got two thetas now, so you want to differentiate between the two. All right, and there's a normal force like this, F normal, and there's two normal forces because there's going to be one over there, so we'll call this one Fn1, and then there's a tension like this because the rope is trying to pull that up the hill, and that's Ft. And there's the free body diagram for number 1. Okay, for number 2, same deal. I won't write in the formulas there. It's kind of hard to do with, the setup that I have here. But there are the two. We'll calculate them using the other whiteboard. Okay, and then you've got a normal force here, and this normal force is going to be a different value. Okay, that's why I'm calling it Fn2, and then there's a tension up like that. Okay, and no friction. All right, like that. Why are these two tensions the same? Why didn't I call this Ft1 and that one Ft2? Well, they're the same because of Newton's third law. Okay. Now the third law says equal in magnitude, opposite direction. And you look at them and you go, well, they're not opposite direction. Yeah, I know, but there's a pulley there. Okay. So I'm kind of hiding a bit of the details. We're not going to worry about what the pulleys do, except insofar as they just change the direction. Okay. So let's get rid of that there. But yeah, that's why this is Ft and that Ft. They're the same values. Okay. They're not different values. All right, so that identifies all the forces. Right now, for question number 1, it's frictionless, and so we don't have to worry about any frictional force. Okay, and the only other thing I'll mention right now before I switch to the other whiteboard is that this force we know is going to cancel against that one, and this one is going to cancel against that one. So when we go to calculate the acceleration, it turns out that we really don't even have to calculate Fn1 and Fn2 or the perpendicular component. We really just need the parallel components, like this one here, and we're going to need that one there. Okay, we don't even need the other one. We will for the other problems, but let's make life a little bit easier. Okay, so let me switch back. Whoops. I should have got this ready. There we go. All right. So now what's the acceleration? Okay, so what we'll do is we'll take a look at M1 first. M1, that was a 7 kilogram. Okay, 7 kilogram like that. And we had, let me cut and paste from this other. Well, I wonder if switching back and forth is going to break things. Let me see, did that, nope, it didn't. Okay, if it does, I'm gonna make sure that, like, if it goes black like that, I'll just keep an eye on it. But this is the parallel component. I even said it there. It's the parallel component. Remember, the parallel component is the sine. Okay. If you want to know why, again, watch the pre-recorded lectures. Okay. So we got M1g sine theta. All right. And again, I should have called it just theta 1 because there are, like I said, 2 thetas, and that one's going to turn out to be 7 times 10 sine of 45 degrees. That's 45 newtons. Okay, there's some decimals there, but I rounded off. Okay, and actually there's more, but let me jump to M2 here and do the same thing for M2. I'll tell you why in just a second. Okay, and for that one, the force is the parallel force here is going to be M2, I guess, theta 2 there. All right, like that. And so we've got M2g sine theta 2, the other angle. Okay, that's 9 times 10. We're rounding off g to 10. We'll do that on the test too. Sine of 30 degrees. Okay, and that turns out to be 50 newtons. Okay, so the reason I did this, because we're not complete with the free body diagrams to get F net for each one of them, but the reason I did that is, let's just go back to this whiteboard. We now know that this force right here, this one is equal to 45 newtons. And we know that this one is equal to 50 newtons. Okay, now why is that important? Because I didn't say yet, we know the system is going to accelerate, but I didn't say yet which direction it's going to accelerate. Compare those two forces. What do you think? Which way is this thing going to accelerate? You say, but I don't know Ft. It doesn't matter. Ft is an internal force, and it'll actually cancel out. Okay, in fact, you'll see that when we go to solve the equations. We have equation 1 and equation 2. Ft will actually drop out. But if you take a look here, the 7 kilogram is being pulled downhill with 45 newtons by gravity, and the 10 kilogram is being pulled downhill with 50 newtons. Well, which one do you think is going to win? I think it's pretty obvious that that one's going to win. Okay. Now, why did I go down that path? Like, why did I reason that out? Because if I ask you which way is the acceleration going to be, that's the direction of the acceleration. Okay. and that's the direction of the acceleration here. Okay. Obviously, if the 10 kilogram goes downhill, it's going to pull the 7 kilogram uphill. If I had just thrown this problem at you, and we hadn't done any analysis at all, you might have said, I have no idea what direction the acceleration is going to be in. Okay, you might have, you might have chosen the acceleration like that way over here and the opposite way over there. But you could tell because you can compare that and that there like that. Now, you might say, well, I might have still gotten it wrong. If you did, if you had chosen A the other way around, then what would happen is your A would come out negative. But, might as well start off with the correct direction for A. And it's not that hard to do. Like when you don't have friction, it's pretty easy to see that, you've got 45 this way and you got 50 that way. So the 50 is going to win. Okay. And that's the direction of the acceleration. So that's why I skipped ahead a little bit just to, show you what was going to happen there. Okay. But let's go back to M1. We got this one and you go, well, what's next? So the whole reason for doing this kind of an analysis, like drawing the diagram, getting the values for the forces as much as we can, is to get F net. Okay, and we'll call this one F net for number 1, because F net for number 2 might be different. And the reason you want F net is because you're going to set that equal to MA, only in this case it's going to be M1A, like that. Why? That's Newton's second law. Whoops, that's the second law. All right. And the whole point of these problems is the second law. But you say, well, what's F net? Well, F net is going to be the sum of the forces. And that's, again, the point of the diagram, because it's going to allow you to, excuse me, it's going to allow you to obtain your net force. Okay. So if I switch back to the diagram and take a look here at M1, okay, the 7 kilogram one. Okay, so the perpendicular forces, they cancel out. The normal force is going to cancel out against the perpendicular force of gravity. Okay, why? Well, if they didn't, then the thing would be accelerating perpendicular to the plane, and it doesn't. Okay, it's not going to levitate off the plane, and it's not going to dig into the plane. So it's not moving perpendicular, and so those two have to cancel. So for F net means add them all up. Okay, that's what you mean by the word net. Those two cancel, so they're out of the picture. The only two that are in the picture are this one and that one. The tension and the parallel component of gravity. Okay, so those are the only two that are in the picture. And then you might say, well, F net, or I guess F net 2, sorry, F net 1 I meant, F net 1, here like that. According to Newton's second law, it has to be in the same direction as A. Okay, so they have to be in the same direction. That means that this force, Ft, must be bigger than the 45. Why? Well, if Ft were smaller, it'd be accelerating in the opposite direction. Okay, well, F net would be in the opposite direction, and it would accelerate in the opposite direction. Because F net is uphill for the 7 kilogram, then this force pulling it uphill must be bigger than the force trying to pull it downhill. Okay, and so over here, what we can say is, okay, so the tension uphill has to be bigger than the 45 newtons downhill. Okay, this equality, that's because of the vector sum. Okay, so students sometimes get confused. You go, well, sometimes you write F net equal to MA, and sometimes you write it equal to the these forces here. Yeah, that's right, because sometimes I'm just invoking Newton's second law, and sometimes I'm invoking the vector sum. Okay, and what you do is you say, okay, well then this, I'll drop the units there, that must equal, and for M1 I must equal this, but for M1 I can put in 7, right, because M1 is 7. All right, and this, if we had Ft, we'd be able to solve it, but we don't have Ft. Solve for A, because that's what I asked for. I asked for the acceleration. Okay, you could solve for A if you had Ft, but you don't have Ft. Okay, and the reason you don't have Ft is because with these problems with two masses, you're going to have to get Ft. You're going to have to get two equations, and then the two equations together will be in terms of Ft and A, and then you can solve. Okay, so once again, how did I get to this? Because that's the critical point here. Okay, one thing was I just did a vector sum to get F net. Okay, and that's that Ft minus 45, and the other side is Ma. Okay, or 7 times A in this case. And so on this side, that's the vector sum for F net, and on that side, that's the MA. Okay, and so this is as far as we can go with that one. All right, so see if there's any questions or if I did anything wrong. All right, you guys look happy so far. Great. Let me do the same thing now for M2. So let's go back to the diagram here. Take a look at M2 here. And for M2, the acceleration is going to be downhill, all right? Because we determined that. And over here, we have what's pulling it downhill, 50 newtons. Now, what's trying to pull it uphill? That FT, okay? So which has to be bigger? Well, for it to go downhill, the 50 newtons has to be bigger than the FT, okay? And so here, F net's going to be this way. Actually, let me rub stuff off here, so don't want to make the diagram too noisy. So this is going to be F net here. And this F net is actually different than that F net. It's F net 2. Okay. But this F net is downhill. So that 50 must be bigger than FT. Okay. In fact, we already have kind of a bound on FT. All right. FT has to be bigger than 45. But it has to be less than 50. Okay, so just remember that when we get FT, we'll compare and we'll see, is it bigger than 45 and less than 50? If it isn't, we did something wrong. Okay, but at this point, all we need is that 50 is bigger than FT because it's got to win over FT to pull M2 downhill. All right, let's switch back here. And so now, when we do FT here, so see, this is what it looked like here. All right, FT was bigger, but now it's the other way around. So for Fnet 2, FT is actually smaller than the 50 newton. I don't know why I'm doing it that way, but there we go. All right, let me get rid of that. The FT, whoops, I really blew it. There we go. Okay, so there the 50 newtons is bigger than the FT, okay? And so now what's that got to equal? So this is the vector sum, and that's got to be equal to, I guess I can do it right here. That's got to equal M2A. Okay, so this equality there, that's true because of the vector sum. This equality there, that's true because of Newton's second law. Okay, so that's going to give me 50 minus Ft is going to equal mass number 2 is 10 times A, and there we go. There's our equation number 2. All right, and the rest is just math. So we'll take equation 1 here. We'll take equation 2. We'll put them one underneath another like that. And this doesn't always work. So maybe I should just say here, solve for A and, whoops, and Ft in 1 and 2. Okay. So this technique I'm going to show you doesn't always work, but it does in these problems. You just add the left-hand side here to the left-hand side there, and Ft will drop out, and you add, of course, the right-hand side to the right-hand side. Okay, so let's do that. We have this plus the other left-hand side here. That's going to equal this plus that. Okay, so why does this work? I don't know. If you're confused with why it works, suppose I have 3 is equal to 3 and 5 is equal to 5. Well, if I add 3 and 3 together, I get 8. And if I add 3 and 3 together, I get 8. Okay, so all you're saying is, look, if that's equal to that and that's equal to that, then this plus this must equal that plus that. Okay, so just a quick aside to say why this technique works. All right, now what? Well, now we notice this Ft is positive, that Ft is negative, so they cancel. So let me do that on the next line here. Okay, so that's going to cancel that one. All right. Negative 45 plus 50, that's just going to leave you with 5. Okay, so 50 minus 45 is 5. And 7a plus 10a is 17a, like that. All right, so basically this whole side just reduces to 5. This side reduces to 17a, and that tells you that a is going to equal, and let me cut and paste the answer here. It's going to equal this. Okay, it's going to equal 0.29. Actually, let me see if there's some extra digits there. Maybe I'll put in another digit so that, because usually I try to keep 3 significant figures, right? We've been trying to do that throughout the course. So it's 0.294. Let's put that in there because that might lead to a round off error later. All right. So there you go. And I also added that it's the 10 kilogram that goes downhill and the 7 kilogram that goes uphill. All right. So that answers the question because I wanted what was the direction. Oh, I also wanted FT. Let's get that too. Okay. So for FT, you could use either equation 1 or 2. It doesn't matter. Okay. You might want to do actually both of them. And the reason you might want to do both is just to make sure that you didn't make a numerical error. Okay. So it might be worth doing both of them. But I'm just going to do one right now. So if I substitute into number 1 here, so find FT. Let me just write it first. Let's see. Find FT by using number 1 here. Okay, so equation number 1 looks like this. Okay, and let me put a 4 in there like that. All right, and that's with A substituted. Okay, so just to remind you, equation number 1 up here, that was this one. FT minus 45 is 7A. So we have FT minus 45 is equal to 7A. But now we know the value of A. All right, and that'll give us FT is equal to 45 plus this right here, and that'll give us that'll give us that FT is equal to, and let me do that on the calculator. That's equal to this, okay? And that's correct, but you know, on a test I always round off, and so that would be like, that would round off to 47.1 like that. Okay, so there's FT. What did I say a minute ago? That FT had to be bigger than 45 and less than 50. It was kind of bound between the two. Okay, and if we go back to the diagram here, we'll see again why. So it has to be bigger than 45. Otherwise, so that I can even write it in. FT here, this one is equal to, what did I just say it was equal to? 47.1. Okay, so this one's 47.1. Yes. And this one's also 47.1. Okay, they're both 47.1. Okay, so 47.1, that's bigger than 45 down here. And yeah, then this would, 7 kilogram would accelerate uphill. Okay, and 50, that's bigger than 47.1. And so yeah, the mass number 2 is going to accelerate downhill. Okay, so that worked out. All right, let me take a quick peek in the chat here to see if there's everyone's doing okay. Everyone okay? Question mark. All right. Well, that answers our first question, and hopefully I didn't go too fast. Like I want you to be able to write these things down, but at the same time, I don't want to waste your time. So there it is. There's equation. There's problem number 1. Okay. Problem number 2 is, whoops, let me switch back here. Problem number 2. Assume only the 7 kilogram mass has static friction. So question number 2 is about static friction. Question number 3 is going to be about kinetic friction. Okay, so that we get everything in here. This question, the reason I picked it or designed it the way I did is because it literally has every possible feature of our Newton's problems that we've done in there. Okay, so assume that the 7 kilogram has static friction, but the 9 kilogram does not. Okay, so the 9 kilogram is still on a frictionless surface, and the 7 kilogram has static friction underneath it. Okay, so how much static friction is there? In other words, how big is the static friction, and in what direction? Okay, and what is the range of the coefficient for the static friction? Now, the reason I asked for the range for the static friction is because the static friction, the formula, let me actually cut and paste it in here so you could see it before I even jump in and start doing stuff. Here's the equation that relates static friction, the coefficient of static friction, okay, to the force of static friction, Fs. Mu s is the coefficient, Fs, and Fn is the normal force, but it's Fn1 because it's the normal force on number 1. But if you take a look at that equation, it's not really an equation, it's an inequality. And the thing about inequalities is that it doesn't solve for what mu s is. It just gives you a range for mu s. So maybe, before we even jump in, just to get the logic right, suppose I said x is bigger than or equal to 5. I just give you that equation. Like, I don't know, the grade 9 math. Solve for x. You go, what do you mean solve for x? How can I solve for x? Because if x is 6, it would work. If x is 7, it would work. If x is like 5.1, it would work. If x is 100, it would work. So there's no 1x value. Like there's an infinity of x values. All you know is that it's bigger than 5. Okay? And so, an inequality doesn't uniquely specify x here. Okay? And so same thing with this. The inequality is not going to specify mu s. All right? So I don't think it's a surprise. There's a question like this on the test. And I say find mu s. And of course, my answers are going to be some value and greater, some value and less than, all those kinds of things. Like you saw that, I think, in the assignment, I gave you something like that. And again, it's a range because you can't uniquely solve from US. All right, anyhow. The 7 kilogram has static friction, the 9 kilogram does not, and I want you to find the coefficient of static friction. All right, so switch back here. Now the diagram is a bit messy. Let me see if I can just erase stuff. I'm just going to go backwards here and start erasing stuff. I think I can do it. There we go. The accelerations are gone, and good. This is good enough here. Okay, this is good enough. Well, I got rid of the accelerations, but it's still good to remember. I guess we're doing acceleration in purple here. It's still good to remember that it really wants to accelerate down this way, and that one wants to accelerate up that way. Okay. Whoops, did I switch? Yeah, I did. Okay, good. So the accelerations do want to go in those directions. Why is that important? Okay, so the only one that has the friction is this one right here. Okay, so there's friction in there, right? 7 kilogram. So there's going to be a frictional force here, and you might say, well, what direction is the frictional force? Is it going to be this way, or is it going to be that way? Well, if without friction it wants to go uphill, then to prevent it from going uphill, the frictional force, I think it's pretty obvious, has to be downhill like that. Okay, and we'll call this Fs, like that. All right, and what's that going to equal? Well, we'll figure that out in just a second. All right, so do you see how I reasoned that out? I said, look, I know there's friction. I know there's going to be no acceleration. Okay, I know the acceleration is 0 here, and the acceleration is 0 there. But if there were no friction, it'd want to go uphill. And so the friction, to prevent it from going uphill, must be downhill. Okay? Now, actually, when you have static friction problems, they're pretty easy. The logic is kind of backwards in the sense that you start from the fact that all the forces add up to 0, and then you can determine any forces that you don't know. Okay, the other way, we had to determine the forces first and then get the acceleration. But now we know the acceleration. Now we can determine the forces by working backwards. So what do I mean by that? Well, this 10 kilogram mass, it's not going up or downhill, right? So what does that mean? That means all the forces downhill must equal all the forces uphill, so that they cancel. But there's only one force uphill, okay? And that is this one, Ft. And you say, well, what must it equal? It must equal 50. Why? Well, because that 50 newtons there has to cancel that 50 newtons. And when all the forces cancel, Newton's first law says when the net force is 0, that meaning that all the forces cancel, you're not going to get you're not going to get any acceleration, in which case it won't go uphill or downhill. These two, they're still around. It's not like they're gone, and we'll actually need them later. But right now, they're canceled. They've canceled against one another. Okay, and so all we had to do is determine. Well, we didn't know that one, but that one must equal that one because again, there's no acceleration up or downhill. Okay, now if this is 50 newtons, if this one's 50 newtons, then guess what? This one must also equal 50 newtons because of Newton's third law plus the pulley. Okay. Okay. So those two are equal to one another. This one is equal to that one. Okay. And now we say, okay, well, you got 50 newtons uphill. That 50 newtons uphill must equal all the forces downhill. And the reason they have to equal all the forces downhill is, again, because there's no acceleration. But gravity is only providing 45 newtons downhill. And so you say to yourself, I've got 50 newtons uphill and only 45 newtons downhill because of gravity. Where is the other 5 newtons going to come? Okay, because the downhill has to equal this again, this part right here that I have circled, okay, that has to equal 50 newtons. You've only got 45, and so you can conclude that static friction must equal 5 newtons. Okay, so static friction is kind of funny. Let me just circle it right here. So there's the static friction. Okay, it's kind of funny in the sense that you don't use the formula from US to calculate static friction the way you do with kinetic. Instead, you just reason it out the way I did. You just say static friction is whatever it has to be such that it doesn't move. And so you got to the point where you said, well, we have got 45, I need 50. What makes up the difference between 45 and 50? That has to be the static friction. And there it is. So the static frictional force is 5 newtons, and it's downhill at the 7 kilogram mass. Okay, so over here I asked, assume that how much static friction is there and in what direction, and now we can answer that. Okay, the force of static friction is 5 newtons, like that, and downhill at the 7 kilogram mass. All right, so everyone good with that? So there's not really a formula. You just have to think it through and say, all right, fine. What value of Fs do I need such that it doesn't move? And there it is. There it is. Okay. Now that answers this part. And now I say, well, what's the range for the coefficient of static friction? So that's this. That's going to give you the range. You have Fs, all right, 5 newtons. But what's that Fn1? You don't have that. Okay. So let's go back to the diagram, and now we can get Fn1. Okay, so Fn1 over here, we said that Fn1 has to cancel that one. So Fn1 must equal M2, sorry, that's a 2, that should be a 1. Oh, I see what happened. The G kind of mushed up against it. Okay, yeah, that's M1G cosine. Oh no, that should have been a theta 1. Guys, I'm sorry. Let me just rewrite this. Hopefully you didn't make that error. This should have been M1G cosine theta 1. Okay, because M1 is 7 kilogram and theta 1 is the 40-degree angle here. Okay, so I don't know. Well, as I was talking, my brain must have drifted. Okay, so anyhow, Fn1 must balance that force. Okay, and so oops. So let's go back here, and we can calculate that. All right. So we're going to need here Fn1, and Fn1 is going to equal M1G cosine theta 1, and that's going to equal 53.6 newtons. Okay. So the normal force for mass number 1 is going to be M1G, but it's the perpendicular component because Fn and the perpendicular component cancel against one another. Opposite directions but equal magnitude, and so that means that Fn1 has to be 53.6. Okay, and so now we've got this. We know that, let me just write it on the next line here like this. We know that that's 5 newtons, and we know that this is 53.6 newtons, like that. And what does that give me? All right, let me get that answer. It gives me this number, but I actually would round it off to that. So it's actually like that. Okay, so mu s must be bigger than 0.0933, and it's dimensionless. Okay, so it's the coefficient of static friction has to be bigger than that. All right, and so that answers question number 2. All right. So let me see. Any questions? Everyone's good. 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 All right. Whoops, and I lost the. But I know the look for this now. So there we go. Okay. So whenever I switch screens, I know to look because I could lose the whiteboard. Okay. So let's move on to question number 3 here. Okay, so question number 3 is assume only the 9 kilogram mass has kinetic friction this time, and that mu k, so mu s is static friction. Mu K is kinetic friction. Kinetic means that it's actually moving, but there's some friction slowing it down, okay? So it's 0.03. Now, this is mu K, and that for number 2, and that one was mu S for number 1. But nonetheless, I mean, in one of my I don't know if it was for your class or not, but in one of the classes, I just made up some numbers and I didn't solve the problem before I actually presented it. And I discovered that I'd made my mu k too big. Mu k has to always be less than mu s, okay? And the reason for that is if mu k were bigger than mu s, then you wouldn't have kinetic friction, because if your mu k is bigger than mu s, then things aren't going to move, and you're not even in a kinetic friction situation. You'd be in a static friction situation. And so mu k is always less than mu s. Now, again, these are not the same, so I'm kind of comparing apples and oranges here, but you can see that I made it small enough. It's 0.03, and the other one was like 0.09, okay? So, yeah, mu k has to be smaller, okay? So let me just move this down a bit so you can see it. So I'm asking, assume only the 9 kilogram has kinetic friction with mu k equals to 0.03. Okay, how much kinetic friction is there, and in what direction, and what is the acceleration, and what is the tension? This question is more like number 1 than it is like number 2, even though 1 and 2 and 3 have friction. This one is actually more like the first one. So let's go back to this diagram right here, and it's getting pretty messy, so I think I'm just going to redraw it, because it shouldn't take that long to just quickly redraw here. So I've got this incline here, I've got that incline there. This one was 40 degrees, okay, and this one was 30 degrees, like that. And then we had a 7 kilogram here, like this, and we had a 10 kilogram here, like that. Okay, so this was the 7 kilogram on this side, and this was the 10 kilogram on that side. Okay, and you kind of want to start over in terms of doing the free body diagrams. Not so much because the forces, there might be extra forces, but the values are going to be different. Okay, so you want to rethink it from scratch. Okay, so over here we had a perpendicular piece here and a parallel piece here. Okay, and the parallel piece, like this one, is calculated m1g sine theta. Sine theta 1. That number is not going to change, okay? Just because it's moving or not moving, the force of gravity doesn't change. And we did that already, so there's no reason to do that again. We know that this is equal to 45 newtons, okay? This one here, we didn't calculate yet. So we'll do that one in just a minute, okay? This one is m1g cosine theta 1, but we don't have that number. Whatever that is equal to, though, that's going to equal Fn1 here, like that. Oh, I'm sorry. I apologize. We do have that one. It's the other one we don't have. We don't have Fn2. Yeah, Fn1 we have is 53.6. I'm sorry, I got a bit confused there. This one we have. So this one we just got. This one was 53.6 newtons, like that. And this one, by just because they have to cancel, has to also be 53.6. Okay, so this is equal to 53.6 here. Okay, and there's tension here, like this, and Ft. Don't say that that's equal to like whatever we got above, because it isn't. It's a different problem. So this one didn't change because gravity didn't change. This one didn't change because gravity didn't change. This one didn't change because it's still balancing gravity and didn't change. This one will change, and it'll change because the acceleration will turn out to be different. And that's it for this one, because the 7 kilogram in this problem doesn't have any friction. Okay, it did in the previous one. I said in the previous problem, number 2, I said the 7 kilogram has static friction, but this time it doesn't. The static friction this time is right here. Sorry, kinetic friction. So that's now the 10 kilogram has kinetic friction. Okay. Oh, I said 9 kilogram in my problem here. No, I meant 10. Okay, so I'll fix it when we switch to the other whiteboard. All right. So so that's it for the forces for the 7 kilogram. Okay, and for the 10 kilogram, we have this one. the parallel component of gravity, hold on, like that. That one was 50 newtons. It's the perpendicular component for this one that we don't have. Okay, so I confused it for this other one a minute ago, but yeah, we don't know this one right now. Okay, we don't know that. We'll get it in a minute, but we don't have it yet. Okay, as a result, we don't have the normal force that balances it. We don't have Fn2. Okay, but as soon as we calculate this perpendicular component here, Fn2 will be equal to it. Okay, we have the tension uphill like this. Okay, Ft, and it's the same value as this one, all right, for the same reasons as before, but it's a different value. It's not going to turn out to be 47.1. It's going to turn out to be a different number, okay? And because there's friction, there's going to be a frictional force. And you might say, well, what direction is the frictional force? But remember, this system wants to accelerate that way. It wants to go downhill, okay? And actually in question number 3, it is moving downhill, all right? But it's not going to accelerate downhill as fast as it did in question 1 because there's a frictional force uphill, all right? So the frictional force, we'll call this one FF, like that. The frictional force is in the opposite direction to the motion, okay? So if it's accelerating downhill like that, then the frictional force is going to be uphill, all right? So good so far. Do you see how I identified all of those? So the two blue vectors there, those are the two components of gravity. Fn2, this one is going to be balancing against the perpendicular component of gravity. There's the tension up, okay, which we don't know, but it'll come out. And there's the force of friction, okay, which we don't know, but we'll calculate in a minute, okay? So this is as far as we can go so far, and now we got to turn to the other whiteboard and do some calculations, okay? So the first calculation that we'll do is, oops, let me just move this down here like that. Okay, the first calculation we'll do is how big is that perpendicular component of gravity for M2? And Anthony, you said would it be 10? Yeah, exactly. So here's the mistake I made, and I just lost it. That's okay. Let me just show you right here. Okay, so if you take a look here, I had written here a minute ago, I'd written 9. I meant 10. I meant 10. I don't know why I had 9 written there, but yeah, I mean, everywhere else we did 10, so we're gonna stick with 10. Okay, so yeah, I'm sorry about that. I don't know what happened when I was typing this up just before the class, but no, it's supposed to be 10. So it's a 10 kilogram which has that. Okay, and so go back to the diagram here. This is 10 kilograms there. Okay, so yeah, thanks for pointing that out. Okay, would it be 10 kilograms? The answer is yes. All right, so let's go back here. So let me grab this, and you know what, I did it wrong right here. We'll fix it. This should be 10, like that. And so this number here, let me work it out. Did I do it wrong above? Oh my goodness. Guys, I really blew it, guys. I really blew it. Look at that. I had a 9 up here. Ah, shoot. I must have changed the number halfway through the problem. Well, you know what? What's broken if I change it to a 9? I should really be more careful. If I make this a 9, so let's change it to a 9 throughout. Oh no, you know what? Look at that. That should have been a 10 there. Because 10 times 10 is 100 times sine of course. Okay, I see what I did. I had 9 and then I changed it to 10. No, you know what? We're good. We're good. Okay. I got a little paranoid there that I was doing things wrong, but no, I'm doing them right. Okay. So yeah, we're good. We're good. We're good. Okay. It's just in my notes I had the wrong number. Okay. So what's this equal to? Okay. So let me work that out. And that is equal to 86.6 here, like that. Okay, 86.6 newtons. And that's the perpendicular component of gravity right there, like that. Okay, and that's also equal to Fn2. So let's go back to the yeah, yeah, Leandro, you're absolutely right. You're absolutely right. Nothing was broken. Yeah, thanks for pointing that out. I guess this is the danger by doing these things kind of extemporaneously. It's I kind of want to work through them with you rather than just having this prepared um, answer. Okay, so let's go back to the diagram here. It's 86.6. So over here, I can write this is equal to over here. This is 86.6 newtons, and the normal force here was 86. Whoops, 86.6 newtons. That's terrible. 86.6 newtons. Okay. All right, there we go. Now we've got the normal force. What about Ft here? Or sorry, Ff. Well, Ff is related to the normal force. Okay, and that's this equation right here. All right, right there. Okay, so unlike the equation for static friction, which is an inequality, okay, technically not an equation, for kinetic friction, it actually is an equation, okay? So if you know the normal force and I give you mu k, you can calculate Ff, all right? So rearranging this, you get that Ff is equal to mu k times, whoops, times Fn2, like that, okay? And that's going to equal what I say mu k was. It's 0.03, like this. And Fn2 is this. And what does that turn out to be? Turns out to be that. Okay, so it's 2.598, okay, and newtons. All right, so if we go back to the diagram, we can actually put in here that Ff is going to equal, this Ff right here is going to equal 2.5, what was it, 598? 598, yeah, 598 newtons, okay? So we've got four of the forces, well, two components and the other two forces. What we don't have is Ft, but you can't get Ft at this point. So you don't have Ft here and you don't have Ft there. It'll come out the same way it did before, all right? So the only other thing to notice here is the 50 newtons down is still going to beat Ft up, but it's going to be beating both Ft and Ff. Okay, so it's going to be 50 newtons down minus Ft minus the 2.598. Okay, so both of them are both Ff and Ft are trying to pull it uphill, and gravity's trying to pull it downhill, and gravity downhill wins. Okay, so over here, I guess we can start off with m2, which is equal to 10 kilograms, like that. We have that F net 2, all right, is going to be 50 downhill minus the Ft uphill minus this, okay, uphill. And there's the vector sum for F net 2. All right, and let me just simplify that, because the 50 minus that you can calculate right away. So let me see what that's going to equal. So that's going to be 50 minus the 2.598. It's this number right here. Okay, minus Ft, like that. Okay, so F net 2 reduces to 47.42 minus Ft. What's that got to equal? These equalities, all this, that's all vector sum up to this point. This next equality, the purpose of it is to equate it to Newton's second law, okay, which is m2 times a, like that, okay? And so this is like F net here. Let me write it like this so you could definitely see what's going on here. So we've got F net 2 is equal to m2 times A. Okay, there's Newton's second law. And F net 2, you say, well, I don't have a number, but you're close. You've got it almost there, except you don't know Ft. And then M2 you have is 10, and A like that. Okay, and that's it. That's as far as you can go. And there you can call this one equation number 1. Okay, and there you go. Now M1, which is the 7 kilogram. Okay, you say, all right, so let's do the dynamics for that one. But that one we kind of did already. All right, let me just remind you what's going on there. Okay, so the Fn1 and the perpendicular component, these ones cancel. So, you know, this is canceling that one. Okay, just like over here, that one canceled that one. Okay, so those two are canceled. So you have 45 downhill and Ft uphill. The Ft uphill has to win. So you're going to have Ft minus 45, and that's going to equal the MA. All right. So we actually have that. I can even cut and paste it from above. That's this one right here. All right. Just like that. So F net for number 1, what does that equal to? Well, it's Ft uphill competing against the 45 downhill, and that's got to equal M1A. And so you get that Ft minus 45 is 7A. And I guess we'll call that equation number 2 here because we called this one number 1. And then we could put the two together. So now solve for A and Ft in equations 1 and 2 like that. Okay. So we have this one and we have this one. All right. And there we go. We'll line them up. Same trick as above. Left-hand side here plus left-hand side there has to equal right-hand side here plus right-hand side there like that. And oh, okay. Now what? Well, let me just copy it here like this. Well, the FT's cancel. You got a negative Ft cancels against the positive Ft like that. And you've got 47 minus 45. All right, what's that going to equal? That's going to equal that. Okay, 2.402. And that's got to equal 17 times A like that. And that gives you an A, which is, so divide that number by 17. And I get that. Okay, and we should round it off to 3 significant figures. So for significant figures, I mean I mentioned it a long time ago, but basically, you know, like anything to the right, sorry, anything to the left at 0, just ignore it, including the, you know, ignore the decimal as well. So this is the first significant figure. There's the second one, and there's the third one. And then if the next one is bigger than 5, then round it up. Otherwise, don't. So it's 141 like that. Okay, everything was in MKS, meters per second squared, like that. And there it is. There's the acceleration. It's the 10 kilogram that wants to go downhill, and the 7 kilogram uphill. Okay, so that solves that one. All right. So let me look in the chat so you can tell me if I've made any other mistakes. Okay, I don't think I did. I think I got it right. It was just because what happened was I switched between 9 and 10, and I changed it in one place, and I didn't change it everywhere. But I think I got it all worked out. All right. Now, before we move on from this question, 1, 2, and 3 are obviously related. Let's see. Does this make sense? Does that make sense? Well, if you go back to question number 1, in question number 1, we got that A was this value here, like that. Okay, so we can compare her. This one was no friction. And if you take a look, yeah, it kind of makes sense because with friction, you're getting 0.294. Without friction, you're getting less, as you would expect. Okay, so the kinetic friction, it's still moving. Okay, so it wouldn't be moving if A were 0. So it is still moving. It's going to start accelerating downhill. But it's not going to accelerate downhill as fast as it would if there were no friction. All right, so there we go. There's questions 1, 2, and 3. And if you followed that, you're really good for the test because this one question kind of covers every possibility that I can ask in terms of the kinds of Newton's law type problems. Okay. Um, the only other thing you really need to know about Newton's laws is you should know their statement, okay, which I haven't done in a live stream, but I did in the pre-recorded lectures. So, just know the statement for the first, second, and third law and what their implications are. So the first law says in the absence of any net force, there's no acceleration. So if you see something that has no acceleration, what can you conclude? Okay, it could be moving, it could have a velocity, but no acceleration. What can you conclude? All the forces have to add up to zero. Not that there are no forces. There might be no forces, but there could be forces. And if there are forces, all the forces have to add up to zero. Okay. So when the net force is zero, there's no acceleration. Conversely, if there's no acceleration, there's no net force. Well, what if there is a net force? Well, then you have an acceleration, and that's the F net is equal to ma. You've seen that a few times already. Okay. And F net and a are in the same direction. All right. And then the third law says that if one thing pulls on something else, that other thing pulls back on the first thing. Same amount of force, opposite direction. Doesn't matter whether one is bigger or smaller than the other one. Okay, so don't get fooled by the sizes of them. I mean, one could be like a large object, another one could be a small object. The forces between them are still the same. So know those, and then know how to solve these problems, and you're good with the Newton's laws. All right, let's go on to, oh, the screen went blank. Well, you know what, that's okay. I was just kind of talking out loud. Let me switch back again. And there it is again. Okay, so I don't know at which point the screen went blank, but I was just kind of talking there about the third law. I wasn't actually typing anything. So all I concluded with was I just said, if we now solve for the acceleration here. Okay, so basically you have the same. Let me scroll back just in case you missed this. So for the first one, for MA2, for M2 equals 10 kilograms, we have that F net was 50 minus the FT uphill minus that extra little bit of force of friction uphill. Okay, and that gave us that it wasn't 50 but 47.402 minus FT. Okay, so that's F net there, and that's got to equal 10A. For the 7 kilogram one, nothing changed from problem number 1. Okay, we had FT uphill and 45 downhill, and that's got to equal 7A. Okay, and when you put the two together like this, all right, you add the left hand side to the left hand side there like that. Okay, and you add the right hand side to the right hand side like that. All right, and you get on the left hand side, you get 2 the FTs cancel out as they always do. You get 2.402 and is equal to 17A, and that works out to that value right there, 0.141 meters per second squared. Compare it to the first one, and it's that. Okay, so let me know if I missed anything in the chat. Did I cover everything that I missed when the screen went blank? If not, just tell me and I can back up. But I think I covered that. Okay, I think I covered from when the screen went blank, and then the stuff that I was talking about with first, second, and third law. I wasn't drawing anything for those. Okay, I was just speaking. All right, so let me just ask here, did everyone get everything from when the screen went blank? We have FB, but what about the tension? Oh yeah, okay, good point. Yeah, let's do the tension. Yeah, so that's pretty easy to do because it's the same as above. You can pick either equation 1 or 2. So use either equation 1 or 2 to solve for the tension. Okay, and so let's pick equation number 2. Let's use that one. And the reason is it just seems a little bit easier. Okay, and you say, well, now what? Well, you know what A is. So you've got this is equal to 7 times A, and A is this one right here. Okay, like that. And that tells you that Ft is going to equal 45 plus this. And that tells you that Ft is going to equal, let me see what that works out to be. It equals this, okay? Newtons. All right, and again, I'd round that off on a test, so that'd be 40. That'd actually be 46.0 newtons, like that. Okay. All right, so that gives you Ft. Let me just show you just to compare it with the Ft from the previous one. So up above here, Ft turned out to be this. So this is with friction, and this one is without friction. Okay, so I'll get rid of the. Well, actually, we could line them up. Okay, so what happened there? They're different numbers. Okay, so that's why there's a danger if you use a number from a previous question when things have changed. Okay, so look at the diagram here. Ft, these two Ft's are equal. Like this Ft here is equal to that Ft there. Okay, just like it was in the previous problem, but they're not the same value. And you say, well, what happened? Well, what happened is because you added this extra force here, your acceleration turns out to be less. When your acceleration turns out to be less, then your Ft has to be less too. Okay. In other words, everything kind of adjusts as a result of adding that extra force. You take that force out of there, you take out this one here, you take out this force here, and you're back to question number one, and then you're at 47.1. But you add that force in there, you decrease the acceleration. You decrease the acceleration, you're going to decrease the tension. Okay. Maybe another way to see it is just concentrate on the 7 kilogram. If Ft is 47.1, the way it was in question one, then you're going to have an acceleration uphill like you did in question one. So in order to have less acceleration uphill for the 7 kilogram, Ft has to be smaller. That's maybe another way to see it. Okay. So yeah, as soon as you start changing any of the forces or adding a force like that, other things will readjust, and so that's why you're going to get a smaller um, force of tension here, like that. Okay. So all right. Thanks for pointing that out, Josh. Yeah, that's a good question to actually answer, because it does show the change. All right. Let me just make sure I answered everything. Uh, Oops, where am I going here? Yeah, that's it. Okay, that's it. All right. So that's it for Newton's laws, and so let's go on to the universal gravitational law and one of Kepler's laws. Okay, so and that'll end it for today. I know I'm not going to get to an energy problem. We did, like I said, we did that last Thursday. And if you want to, you can come to the Physics 101 tomorrow if you can make those, or just watch them afterwards. I'm basically just going to do an energy problem for them. Okay, so let's take a look here at what I ask. What is the gravitational force between two 1 gram masses? So I have a 1 gram mass here and another 1 gram mass here, and they're a centimeter apart like that. And I ask, what's the gravitational force between them? Okay. Now remember what Newton's universal gravitational law says. It says between any two masses in the universe, there's an attractive force, the force of gravity. The thing is that the force of gravity is a really small force. There's actually four fundamental forces, and of all the forces, the force of gravity is by far the smallest. Okay. And so, like, it was very hard for people to discover the force of gravity. I mean, I know people know that things fall, but they didn't think about it in terms of forces, and that's because it's a tiny force. So you don't feel like, when you walk beside your car or something that you're being gravitationally attracted towards your car. That's because you're relatively small and the car's relatively small. Okay, we don't think it's small, but on the size of gravity, yeah, it is small, and so you don't feel that the car is kind of pulling you towards it. So I just was going to show you how small the force of gravity could be. So a little 1 gram mass, okay, and then you got another 1 gram mass, and they're a centimeter apart, okay, and you say, well, how much gravity do you have? And you need also, for these problems, you need this number here. It's called the universal gravitational constant. universal grav constant, like that. Okay, of course I would give it to you. I would not expect you to memorize that. And the formula that you use is basically this formula here. Let me cut and paste it. It's this one. Okay, like that. All right. So it's basically F is equal to G, capital G, okay, not little g, m1, that's one mass, times m2 divided by r squared, where r is the distance between the two. And if you wonder, like, is it the distance from the edges or from the middle, it's actually the distance from the middle to the middle, okay, of the two objects. All right. And if we substitute in the numbers here, okay, you're going to get this, like that. All right. So, so I hope I'm not going too fast. But I don't feel like typing this out. It takes a while. So there, what's this? That's the universal gravitational constant. It's the number I just gave you. And the units are Newton meter squared. You have to convert it to kilograms, okay? And 1 gram is a thousandth of a kilogram, so it's 0.001, okay? So here's 1 gram. That's M1. M2 is also 1 gram. And they're a centimeter apart. And for R here, we have to work in meters, okay? And so 1 centimeter is 0.01 meters, like that. All right. And you have to square it because it's r squared. Now, if you work that out, you're going to get an absolutely tiny number. You're going to get this number right here. 6.67 times 10 to the minus 13 newtons. Now, you don't even know what minus 13 newtons is. Like minus 10, I'm sorry, minus 9, just 10 to the minus 9, that's 1 billionth. 10 to the minus 12 is 1 trillionth. And this is a tenth of a trillionth. So it's absolutely tiny. It's unmeasurably small. You couldn't possibly measure this in the lab. All right. And so just to compare, I said, well, okay, fine. Let's calculate the force of gravity between the Earth and the Sun. All right. So the same formula, but now for the mass of the Earth, you're going to use this number right here. Okay, I just Googled for it. I would never ask you to memorize any of these numbers, okay? So, it is an open book test, so you could Google for it, but I wouldn't do that. I would give you these numbers. So there's the mass of the Earth. There's the mass of the Sun. I just Googled for it before class, okay? And this is the distance between the Earth and the Sun, okay? I called it RES. ES is Earth, Sun, okay? And this is the way it actually came up in Google. It was 148.65 million kilometers. Okay. Now we do want the masses in kilograms, but we want the radius in meters, not kilometers. Okay. And so this number here, maybe I should do it on another line here, like this. This number here, we're going to write as this. Okay. Now million is times 10 to the 6. Okay, but that's still in kilometers, right? Okay, so what's this 10 to the 6? That's the million. And to get rid of the kilometers, k is 10 to the 3, so that's going to be 10 to the 3, like that. Okay, and that's how we're going to convert it to meters. Okay, and so I just substituted in there. I mean, you have to do it carefully. Because you can obviously type this into a calculator wrong. So you just have to, that's the only tricky part of this. Let me get rid of that because, well, actually, I don't need to get rid of that. It's the same formula, okay? Same formula, but, so there's G, the same value of G. G, that's what we mean by the word universal. It doesn't change. There's the mass of the Earth. There's the mass of the Sun. And there is this number right here, okay? So actually, I could write it as just that K there for kilometers, kilo. The kilo part here is 1,000. There it is there, okay? So some spaces in there. All right, and what does that work out to? Well, now you're not going to get a tiny number. Now you're going to get a big number. There it is. Okay. So 3.59 times 10 to the 22 newtons. Now, the previous number was so small that it was unimaginably small. This number is so big, it's unimaginably big, okay? So when you have big masses, like things the size of the sun or the size of the Earth, yeah, then you're going to have gravitational forces that are measurable. Okay, but when there are things that are like this, 1 gram or even the size of your car, that's why you don't feel the force of gravity. Okay, so I just thought I'd do that to give you a sense about like this force of gravity. And yeah, it's big between planets, but it's small between regular size objects. It's actually kind of big between you and the Earth, not because you're big, but because the Earth is big. Okay, and so there's a force of gravity there. All right, so that's the universal gravitational law. And the last one I'm going to do for you is, let's see, how am I doing for time? Okay, we're almost done here. The last one I'm going to do is this one right here. It's Kepler's law problem, and it's pretty easy. It's just you have an asteroid, and I'd say that it takes 565 days for the asteroid to go around the sun. Okay, and how much bigger is the asteroid's orbit? Uh, um, is the how much bigger is, I didn't write it right. How much bigger is its orbit than the Earth's orbit? Okay. So how much bigger is the orbit? Well, for that one, you use Kepler's third law, because what does Kepler's third law do? It relates the radius of the orbit to the period of the orbit, okay? And it relates it for different planets, and so it looks like this. Oh, I didn't write it down. Okay, I don't have it ready to cut and paste, but it looks like this. You have radius of the Earth cubed divided by the period of the Earth squared. That's going to equal the radius of the asteroid cubed divided by the period of the asteroid squared, like that. Okay? So now what? Well, we can just put in the values here. The only thing is you say, well, what should I use for the radius of the Earth? And the answer is you could just use 1, because all you want is the percentage bigger. And so if you say the Earth's orbit is at 1 unit, now this is the kind of trick in this problem. If you say the Earth's orbit is 1 unit, well, then whatever number you get out is going to be, like say it's 1.5, then it means it's 50% bigger. Okay, you'll see what I mean by that, okay, in a second. You don't actually have to put in the Earth's orbit there, which is this number up here, okay. You could just go right ahead and say, you know what, the Earth's orbit, I'm going to just put in 1, like that. So that's going to be 1 cubed. All right, now what's the period of the Earth in days? How long does it take the Earth to go around the sun? Well, 365 days. So over here, you would just do 365 squared. And what's that got to equal? Well, that's going to equal the radius of the asteroid cubed. Well, that's what we want. We want the radius of the asteroid, okay? Divided by the period of the asteroid, and I tell you what that is. That's 365 days, okay? So this is Kepler's third law. And to use Kepler's third law, I got to give you 3 of the 4 things. And the thing that I didn't give you here is the radius of the asteroid's orbit. Okay, so how much bigger is its orbit, or the asteroid's orbit, than the Earth? So you're solving for the asteroid's orbit here. The trick is that since you want an answer as a percentage, don't worry about having to actually put a number in there, because you're going to do a ratio at the end anyhow. Let's just calculate that. And so this one is going to equal, well, if I just cross multiply here, I'm going to get this, like that. And then over here, let me multiply both sides by this. Okay, like that. And that tells me that here I'll get that very quickly in my calculator here. Oh, didn't work. Copy, paste, and I get this is equal to that. And then RA, you want to do the cubed root. And the cubed root is, if you take this, if this is to the 3rd power, then this one you want to do to the 1/3 power, like that. Okay, that's how you can do a cubed root. All right, so what's that going to equal? Well, I'll tell you in a second. To the exponent 1 divided by 3, it turns out to be this. Okay, that number right there. Now, last thing, how do I answer the question? How much bigger is it? An answer as a percentage. Well, if the Earth's orbit is 1, that's actually called an astronomical unit, but you don't even need to know that. Just say it's 1. We're just going to make up a new unit. We're going to say it's 1. Well, if the Earth's orbit is 1, then how big is the asteroid orbit? The asteroid's orbit is that. Okay, so it is 0.338 bigger, okay, or 33.8% bigger. Okay, so that's how you answer that one. I mean, I probably would word it a little bit better on a test, but that this is basically how you do it. You just compare the two, okay? And if the Earth's orbit is 1 unit, the orbit of the asteroid would be 1.338 units, okay? And that basically makes it 0.338 or 33.8% bigger. All right. So let's see if there's any questions with that one. But that's an example of using the third law, okay, Kepler's third law. All right, so Kepler's third law, once again, is basically this one right here. What it does is it relates the radius and the period of orbits, okay, and uh, that's the third law. The other two laws are pretty simple. The first law, the shape of the orbits are oval, are ellipses, okay, with the sun at one of the focal points. I can't ask you to do problems with that. You just need to know them. And the other one, the second law, basically says that it sweeps out an equal amount of area in an equal amount of time, which qualitatively means that the planet travels fastest when it's closest to the sun and slowest when it's further from the sun. Since the orbit is an ellipse with the sun at one of the focal points, what that means is that it's actually going to be sometimes closer. The planet's going to be sometimes closer and sometimes further away. When it's closest to the sun, it's moving fastest. When it's further from the sun, it's moving slowest. Okay, so I rushed a little bit there at the end, but I think that pretty much covers what I wanted to do. If you have any questions, I've got a few minutes here before I have to go start the stream for the next class. But any questions, or are we good? All right. It doesn't look like I've got any questions. Hopefully, I didn't go too fast there. But there's Kepler's third law right there. Okay, that's the only one I could really ask you to solve problems. The other ones you just have to know about. All right. I've got an okay. So, all right, I'm gonna end the stream right now, and if you have any other questions, catch me during my Google Hangouts. If you do want to see yet another energy problem, like I said, you can join. Feel free to join one of the. I'll probably put that in the email. Feel free to join any one of the Physics 101 tomorrow. And if I do mention any calculus, I'll make sure that I very specifically say. This is only for 101, not for 111. Okay, so I won't confuse you. Okay.